the regularity condition, plus a radial velocity field, which is also 0 at the center. And plus, there are some additional regularity conditions on the derivative at the center, which, however, I haven't written here in this list. And by self-gravitating, I mean that this Euler state variable, the mass density, the radial pressure, the tangential pressure, and the velocity field satisfy this equation. So the first equation is just the continuity equation for the mass density. And the second equation is the balance of momentum. So on the left-hand side, we have the convective derivative of the momentum, essentially, so the acceleration. And in the right-hand side, we have the forces which act inside the body. And there is the first term, this one, is due to the internal strain in the body, while this second force is just the gravitational force self-induced by the body on itself. And this small r is, as usual, the local mass. So it's the mass of the body in a sphere of radius small r. And this system is supplemented with the two standard boundary conditions. So first, assume that the radial pressure on the boundary is 0, which means that I'm assuming here that this ball of matter is surrounded by vacuum. And then the velocity field on the boundary must satisfy this equation. So ut evaluated in RT must equal to the derivative of RT. And it's the condition that the boundary is comoving with the matter. So in particular, there is no mass flowing out this ball. And therefore, because of this boundary condition and the continuity equation, the mass of the ball is at least formally conserved. And so of course here we have 4 variables and only 2 equations. So we need an equation of state between at least the first 3 variables to close the system. And a very popular example in astrophysics is the equation of state of polytropic fluids, which I write in this form. First, I introduce the number density of particle, which I denote by delta, and a constant K, capital K, which is the mass of the fluid particle. I'm assuming here that this fluid is homogeneous, so it is made of only one species of particle with mass capital K, and then I write the mass density as this K multiplied by the number density of particle. And because it's a fluid, then only isotropic stress is allowed, which means that the radial pressure and the tangential pressures are the same. And in the polytropic case are given by this power law, okay? So of the density. So in this expression, K is called, so kappa is called the bulk modulus of the fluid, and gamma is the adiabatic index. So kappa, the bulk modulus, is a material parameter, so it depends on the specific fluid material, while gamma is an equation of state parameter. Okay, so I can fix capital K, so I fix the fluid material and change gamma, so but having the same material, depending on the response of the material, of the fluid to deformation. And so the purpose of my talk is to extend this polytropic equation of state to the case of spherically symmetric elastic bodies. We have seen already many talks in this conference that focus on the polytropic fluid. So it seems natural that if one wants to work on elastic matter, then I mean, the first thing to try would be maybe to start this generalization of the polytropic equation of states, the case of elastic matter, because then one can expect that this equation of state will enjoy similar properties as the polytropic fluid. Okay, so then the first thing you need to know about elastic matter, if you are not already an expert on this, is that we need more than just one material constant to specify the material of an elastic body. We need at least 2 material constants. And for instance, a very standard choice is to take this to be the Lamé parameters, which are denoted by lambda mu. But for the purpose of my talk is more convenient to choose instead of lambda nu the bulk modulus K, so the same that we had in the fluid case, plus the Poisson ratio, which is denoted by mu, and it's a dimensionless number that lies in the interval -1 and 1/2. And this choice of a set of parameters are completely equivalent because these parameters are related by this equation here. So the most important parameter here is the Poisson ratio. The bulk modulus, you can always set it equal to 1, like everyone does in the fluid case, but the Poisson ratio, the value of the Poisson ratio is important. So it affects strongly how the material behaves. So what is the interpretation of this Poisson ratio? You can see in this picture. Suppose that you take a cylinder of this given elastic material and you apply a small up. Can you hear me again?
Yes, we can hear you, but it seemed that as if in between the sound was even better.
Okay. I think there was a problem with my speaker or my headphones. But okay, so we applied a small force on the top of the cylinder, and then it will deform into a direction, into two directions: direction longitude parallel to the applied force, and also on the plane orthogonal to the applied force. And if this deformation is small, this formation are small enough, then we can apply linear elasticity to describe them. And in the linear elasticity theory, the expansion here in the orthogonal direction is proportional to this Poisson ratio mu. And in this table, I show you some example of mu for some materials. In the fluid case, the Poisson ratio is always equal to 1/2. In fact, this can be used as a definition of fluid in the class of elastic material. So an elastic fluid is an elastic material with Poisson ratio equal 1/2. And there are also materials with negative Poisson ratio, but I haven't listed any in this table. And then, for instance, you see cork has a Poisson ratio equal to 0, which explains why cork is such a good material to seal wine bottles, for instance, because then when you insert the wine opener on the top, the cork will not expand in the orthogonal directions, and therefore it's easier to remove the cork from the bottle. Okay, so that's the first difference from elastic matter and fluids. In elastic matter, you need at least one more material parameters, which I will take it to be this Poisson ratio. And the second difference is actually in the formulation itself originally of the theory, because while fluid mechanics is originally formulated in Euler space, elasticity is, on the other hand, originally formulated in Lagrangian coordinates. Okay, and this is because in elasticity theory, it is assumed that the stress accumulated in the body depends on the deformation of the body from a given reference configuration. So if we talk about a body that has been deformed, we of course to specify first a reference state, which we could say before the body has been deformed. And so if we denote by psi, this is called the formation function. So it's a function that maps point in the reference state of the body before the formation to the new position in the deformed or physical state. Then the Euler state variable are related to this deformation through the equation that you can see here. Okay, so in particular, the stress, this radial and tangential pressure, are function of psi and the deformation and the deformation gradient. And in this equation here that I wrote, so the left-hand side is evaluated on the deformed state. So this rho, p rad, p tangent, and u are functions, as I showed before, of the small r, which is a radius in the deformed state, while this the right-hand side is evaluated in Lagrangian coordinates, in coordinates in the reference state. And if you now take this the Euler state variable expressed in this way, replacing the Euler equation that I showed before, then you will obtain a nonlinear. Well, in general, it's a system of nonlinear wave equation, but because we are in spherical symmetry, just one nonlinear wave equation on this deformation function defined in the reference configuration. So this is the standard formulation of elasticity theory for spherical symmetric bodies. But this formulation is problematic, in my opinion, for the application to astrophysics for some reasons. The first reason is that this reference state of the, I mean, in astrophysics, of course, the body of interest are like planets, stars, or galaxies. And for these bodies, it's, I mean, it's difficult, at least, to define what is a reference state. In particular, the reference state is usually assumed to be stress-free, and it's hard to imagine how can one actually define physically a reference state for this astrophysical object. Definitely, it's not an observable state. And the other reasons, because I find that this Lagrangian formulation is problematic for in astrophysics. So for this problem of self-gravitating bodies, is that it's hard to reconstruct the properties of these bodies in physical space from the properties in the reference state. Yes, and eventually we want to do that because astrophysicists are interested in the properties of a star in the space where we observe it. Okay, so in the physical space. And but as I said, it's difficult to translate properties from the reference configuration to the deformed state, because in general, this deformation function solution of this nonlinear wave equation is not a smooth math. I mean, first of all, you have to prove that it exists. And then even when it exists, usually, at least for large deformation, you cannot expect to be a very smooth function. And here in particular, in this talk, and for the application to astrophysics, I think that it's really important to be able to handle large deformation, because of course the stress inside astrophysical bodies is very, very large.
Can I ask you something, Simone?
Sure, Ben.
Could you not just treat the thing as an anisotropic fluid, which just would mean that you have the tangential pressure and the radial pressure, and you need an extra piece of equation of state for the tangential pressure, and then you have precisely the equation you started off with?
Yes.
Is this what you have in mind, basically?
Well, these equations here, these are the general equation. I mean, any spherical symmetric matter, regardless of whether it's a fluid or elastic material and so on. I mean,
but I would call this an anisotropic fluid.
Well, I don't
because there's no reference configuration.
Well, not yet. I mean, there is no reference configuration because this is formulated in Euler space, but there will be an Euler formulation, sorry, a Lagrangian formulation equivalent to the one that I'm going to talk about.
Okay, thanks.
So, right, I should say that, I mean, I'm not claiming that the Lagrangian formulation should not be used. I mean, it's, and in particular, Robert Bike and Ben Schmidt have written a series of papers where they analyze the problem of self-gravitating elastic bodies in the reference state and Lagrangian coordinates. I believe the one that I cite here is the first paper in the series, and this work by Bobby and Ben is extremely important for me personally, because that's how I got interested in the problem, by reading the papers. And also because besides the fact that they prove impressive results, it's also important here that I say that Bobby and Ben have brought this topic into our community, to the gravitational community. And I hope that, I mean, I might also contribute somehow to make this problem interested for also the other colleagues in this community, for all of you. And but you know, besides all this love and respect that I have for your work, Ben and Bobby, I'm going to do it a little differently. As I said, I want to have I want to study this problem of self-gravitating elastic bodies now just in spherical symmetry by using just a Euler formulation of the problem for the reason that I just mentioned, because I want to have a formulation that can be possibly used by astrophysicists also to study property of the elastic bodies in physical properties. Okay, and not just it's not just a mathematical problem for me. And so then in a recent paper, Artur, Alio, and myself, we have introduced a formulation of elasticity theory, which for the moment is only for spherical symmetric bodies. And I'm going to present this formulation in 3 definitions. So the first definition is actually the, and I think this will answer also Ben's question, is the what I mean by a constitutive function of spherical symmetric elastic body in Euler space. So I assume that I have 2 constants here given, like the modulus k and the Poisson ratio, which is the number between -1 and 1/2. Then I say that an elastic constitutive function for spherical symmetric body with bulk modulus k and Poisson ratio mu is a map, a smooth map, p rad p tang from 0 infinity square to R2, such that this map satisfies the following equations here, 1, 2, and 3. So let's see what this equation means. So the first equation, means that if I evaluate this constitutive function in delta delta, that they have to be equal, and also this other identity has to be satisfied. So what does it mean? This still, I mean, when I apply this constitutive function to the special case of a ball, then we will see that for a ball, this variable delta and eta must be equal at the center. Okay, and so then this equation 1 is just a regularity condition for one way you can interpret this equation 1 is that it's a regularity condition on the center of the ball when you apply this constitutive function to a ball. Okay, because for instance, I show at the beginning that one of the conditions, the regularity condition for a ball of matter, whatever is the material, is that the radial and the tangential pressure should be equal at the center. And while these 2 equations here, 2 and 3, they are evaluated, they are conditioned on the derivative of the radial and tangential pressure evaluated in delta equal eta equal 1. So what is the meaning of this? So because of this equation 2 and 3, the Taylor expansion at first order of all constitutive functions is the same, right? If we because the derivative in 1, 1. So if we Taylor expand any constitutive function around this state 1, 1, then we obtain always the same linear approximation, right? So this equation 2 and 3 therefore translate in our formulation the postulate somehow that in elasticity that every material should obey Hooke's law of linear elasticity for small deformation. Okay, so this state 1, 1 corresponds in this formulation to the Lagrangian formulation, so the reference state in the Lagrangian formulation. Okay, so when I expand, so when I take small deformation around the reference state, then linear elasticity should apply. This is the meaning of this equation 2 and 3. And this is also what I write here in this remark. Okay, maybe there is something more to say about this equation actually. So because of this first equation in 1, the radial. So when I set delta equal 1 in this equation, then the radial pressure and the tangential pressure are equal in the reference state. So the reference state is isotropic. However, so let's call P these common values of the principal pressure on the reference state. If this P is equal to 0, then the reference state is said to be a natural state. Yes, it's a stress-free reference state. And this case is included in this definition, but I'm not imposing here that the reference state should be stress-free because of a reason that will become clear later. Okay. And the other thing I could say is that, so if you take now this radial pressure and the tangential pressure to be just a function equal and to be just a function of delta, then necessarily the Poisson ratio is equal to 1/2. I mean, you can see it from here, right? If the derivative in eta of the P rad and P tangent 0, then nu must be equal to 1/2. So this corresponds to the case of a fluid constitutive function. Okay? So a fluid constitutive function is a special case of elastic constitutive function. And well, I already mentioned this special case of this polytropic fluid. So now there is a special case of this elastic materials that is perhaps the most, if not the only important one in the application, so which are the so-called hyperelastic materials. So material is said to be hyperelastic if there exists a function w hat of delta and eta, such that I can write the constitutive function for the radial pressure and the tangential pressure using this formula that you can read here. Okay? And this function w hat is called the stored energy function of the material. So these are the most important for several reasons. First of all, W is the energy of this elastic body. Okay? So if the material is not hyperelastic, then you cannot define an energy for the elastic body. And then to be able to define the energy of the elastic body is, of course, very important. For instance, it can be shown that, at least formally, the static solutions of this problem can be, so they are at least formally minimizer of the energy function. So, but if you don't have an energy, then you cannot even make sense to this statement. And also, of course, for in general activity, these are the only materials that make sense because the energy density W appears in the Einstein equation as a source of gravitational field. And so now these are just the definition of a constitutive function, general definition, and a particular case of hyperelastic material. So now let me say what does it mean that a ball of matter is an elastic ball of matter? Well, a ball of matter, which I said is described by these four Euler state variables, is said to be a homogeneous elastic ball with particle number density delta if there exists an elastic constitutive function as defined before, and a constant capital K, which would be then the mass of the body particle, such that the following equation of state holds. Okay? So the mass density is K, the mass of each body particle times the number density of particles, and the radial pressure and the tangential pressure at the radius small r is obtained by evaluating the constitutive function on delta, on the density delta, and this function eta, which is defined in this way. Okay, and what is that? Is just the average particle length, average particle number density in a ball of radius small r. Okay, so as you can see, this is just density. So the integral over a ball of radius r divided by the volume of the ball. And so this is in the case of a ball, because we are in spherical symmetry, then a single body is either a ball or a shell. And so this, what I'm giving here is the definition of an elastic ball, because that's what I'm going to focus in this talk. But you can define in a similar way also what an elastic shell is. The only difference is the definition of the function eta. Here, because I'm in the case of a ball, then I'm integrating from the center, start from 0. But when you have a shell, then you start integrating from a positive radius, which will be the inner radius of the shell. So then we can, so now we have only two independent variables, right? Delta and u. So now I can rewrite this Euler equation only in terms of delta and u. And so the first one is just, again, the continuity equation that now I express in terms of delta instead of rho. And then in this equation here, so that I define this A hat is the derivative of the radial pressure with respect to the density, and this function B is this long expression of in terms of the tangential pressure and the radial pressure. So for in the fluid case, this B is equal to 0. Okay, so this is the new term which appears because we are studying a anisotropic material, and the boundary conditions are just the same as before. Now the first one becomes a nonlinear boundary condition on the density delta. And so not all these constitutive functions are good from a physical or mathematical point of view. There are some constraints that one has to require, and some are mathematically justified, others are more physically motivated. So I think start with one which is more mathematically motivated. And that is, as you said, this is the same as for proof. Okay? I'm not discovering anything new here. So you can rewrite this Euler equation here as a system in terms of delta, eta, u as a system of conservation laws. And then you find that the condition for these systems to be hyperbolic is that the derivative of the radial pressure in the density should be positive, which of course is satisfied in the case of polytropic fluids in the interior of the body. But now I'm going to require it also. I mean, in the generalization of the polytropic fluid to the elastic case that I'm looking for, I want this condition also to be satisfied. Okay? So then I say that an elastic cosmic function is globally strictly hyperbolic if this inequality is satisfied for all delta and eta positive, and also for all k and all Poisson ratio. Okay, so I don't want this constitutive equation to be globally strictly hyperbolic only for one material, so for one value of mu, and not for other materials. So this is the first inequality that is natural, I mean, to impose on this constitutive function. And the second one is it's called, I mean, there are many of these in elasticity theory, but the one that I'm going to use is the so-called Bacher-Erichsen inequality. And what does this Bacher-Erichsen inequality mean? I don't really have time to explain this too much in details, but the idea here is that the Bacher-Erichsen inequality means that the deformation in the interior of the body along each principal direction increases with the intensity of the applied force. Okay, so the stronger is the force that you apply in one direction, the more the body will deform in that direction. And that is, I would say, a rather intuitive and reasonable condition to impose. And in this formulation of elasticity for spherical symmetric body that I just mentioned, so that this Bacher-Erichsen inequality takes the form that I will show you now in the next slide. And actually, I need to it's convenient to me to consider two versions of this inequality. So the inequality is the one that you see here. So the tangential pressure delta eta minus the radial pressure in delta eta should divided eta minus delta should be positive. And then if it is positive for all delta and eta positive, I call this the strong Bacher-Erichsen inequality. While if it's positive at least only for eta greater than delta, then I call it the weak Bacher-Erichsen inequality. And the reason to distinguish between this is that, as I will show in a moment, in the static case, or in the important case of static bodies, then the weak version of the Bacher-Erichsen inequality is the only one which actually matters. So now I think I have an example here to show, an example that is known. So this is one of the most popular material models. It's very old. It goes back to Berns and Kirchhoff, so it's 150 years ago or something. And so this is not the general stored energy function of Berns Kirchhoff materials, because I'm in spherical symmetry. Okay, so that's only in the spherical symmetry case, and it is in our formulation of elasticity theory for spherical symmetry. So as you can see, it's a not very nice looking equation. And here I also, maybe the only thing I should mention here is that I write this stored energy function in such a way that this variable y, which is delta over eta, appears, because as you will see, this play a fundamental rule. So I call this the shear variable, okay, this variable one. And it turns out this Berns Kirchhoff model is neither globally strictly hyperbolic nor satisfy the Bacher-Erichsen inequality. In fact, the region where these two conditions are satisfied in the delta eta plane, you can see them here. So the left is the region where the hyperbolicity condition is satisfied, and the right is the region where the Bacher-Erichsen inequality is satisfied. So they're not satisfied for all delta eta, but they are satisfied if you take a neighborhood of the reference state, okay, which I remind you in this formulation is the state delta equal eta equal 1. So as long as the deformation is not, then this model, so as long as the deformation is not too large, then this model is admissible. I mean, in the sense that it satisfies this inequality that I just presented. Okay, and I should say that this Van-den-Ham-Kirchhoff model is known not to be a good model for large deformation. It was, but because usually you see in the application, the standard application of elasticity theory in engineering and material science, so in this community they are not so much interested in very large deformation. But because in the problem of self-gravitating bodies, I want to have a constitutive function, a storage function that preserves these properties even for very large deformation. I don't want to limit myself to small, even finite but small deformation. So then maybe this time to small remark in the case of static self-gravitating balls. Then in this case, the Euler equation just reduced to this equation on the density. So it's an ordinary differential equation on the density. Again, the new term is this one with B. If B is 0, then you are in the fluid case. And here is what this Bacher-Eriksson inequality actually is important, because it can be shown that for static self-gravitating elastic balls, if the constitutive function satisfies the weak Bacher-Eriksson inequality, then the tangential pressure is greater than the radial pressure everywhere in the interior of the ball. And the proof is 4 lines, so I can give it to you. It's an easy continuation argument to prove that solution of equation phi satisfy eta greater than delta as long as they exist. And so, but now, so eta is greater than delta, but now the Bacher-Eriksson inequality says that if eta is greater than delta, then the tangential pressure must be greater than the radial pressure. Okay.
What happens? What happens at the center? At the center with the pressure?
At the center, eta and delta are equal. Okay. So in the center, eta and delta are equal, and then the radial pressure and the tangential pressure are equal.
Okay. Okay.
Mm-hmm. So because this, remember, eta is the average particle density. So if you let R to 0, the average particle density will just equal.
I overlooked that you have the open interval there.
No, it's an open interval. Yeah. It's an open. So then this is so why this is important, by the way, because you see because then if you want to prove the existence of this static self-gravitating balls, you have to show that this radial pressure is positive in the interior, and then it becomes 0 on the boundary. But then you should also prove that the tangential pressure is positive, and this is actually the most technical part of the proof, because the tangential pressure usually is very nasty as an equation. So, but thanks to this Bacher-Eriksson inequality, you don't need to do that, because if you prove that the radial pressure is positive in the interior, then the tangential pressure will also be positive. So now a remark on homologous elastic ball. This homologous solution has been discussed already also in some talks in this conference, and they are defined by requiring that the velocity field has this particular form, so it separates the dependence on time and R. I mean, so of course this, in general, I think this is somehow the equivalent of this Oppenheimer-Schneider solution for the collapse of a homogeneous ball of dust. And so here, if you replace this velocity field in the continuity equation, then you will derive that the density and the average particle density have this form here, where delta 0 is just, because I'm assuming that, say, without loss of generality, that omega 0 is equal to 1, then delta 0 is just the initial value of the density, and eta 0 is also the initial value of the average density. And so I want that, because this solution exists in the polytropic fluid case, so I want this to exist also in the elastic case. So, but then there is this constraint, this other constraint to the possible elastic positive function, because so if you see the boundary condition on the velocity field defines this radius of the ball to be just omega t times a constant. Okay, so and then if we evaluate this shear variable y on the boundary, so at r equal rt, this is delta over eta evaluated at rt, and because delta and eta have this particular form, and the small r is a constant times omega t, then what you get is something constant. Okay, so that's not dependent t. Okay, so the only elastic constitutive function which may give rise to this homologous balls must have constant shear on the boundary. Okay, so the boundary ball must have constant shear. And of course, then the constitutive function for the radial pressure must be consistent with this property if I want the other boundary condition to be satisfied. And so P rad at RT must be 0. But now P rad at RT is just because at RT delta is YB times eta. So then this has to be satisfied. Okay. So this has to be 0. Okay. And this necessarily, because this has to be 0, and I want this to be 0 for all possible value of this eta, because otherwise it means that, I mean, otherwise, since eta at the boundary is essentially the total mass divided the cube of the radius. If it's not true for all eta, then I just have the only homologous solution would be the static solution. So then I will require that my polytropic elastic, let's call it constitutive function, should satisfy this constant boundary shear assumption, namely that there exists a unique YB greater or equal to 0, such that P rad YB eta is equal to 0 for all eta. And then the other condition, I've mentioned this very quick, is that, of course, there should also be a scale invariance in the Euler equation. And it turns out that to admit the possibility of self-similar collapse. And now here, actually, I'm setting, when I write, this is the scaling condition that you need in the Euler equation to have self-similar solution. Actually, here I'm assuming that G is 0, so there is no gravity. So because I'm only interested in a property of the matter model. Okay. So if you want the Euler equation for the elastic body without gravity to be to admit self-similar solution to be scale invariant, then you have to require that this function A and B should satisfy this scaling property. And now here is there, I say this because there's an important remark I should mention, that if you want a spherical symmetric body to satisfy both the CBS condition, so the constant boundary shear assumption, and this scaling symmetry assumption, then it cannot have a natural reference state. That is why from the beginning, I did not impose, as it is usually do in elasticity theory, that the reference state should be stress-free. Okay, so now it turns out, it turns out that's kind of obvious that in the fluid case, the CBS condition is just the condition that the pressure has to be 0 when the density is 0, okay, which is of course satisfied by the polytropic equation of state. And so if you require that the pressure is 0 when the density is 0, and also the equation should be scale invariant, that the only possible equation of state that you have in the fluid case is the polytropic fluid equation of state. Okay? So then I just use this to define what I mean by an elastic constitutive function is a generalized polytropic elastic constitutive function if so the constitutive function is hyperelastic, globally strict hyperbolic, and satisfy the scaling symmetry assumption, and also satisfy this constant boundary shear assumption. Okay, so then in the fluid case, there is only one such constitutive function, which is the constitutive function of the polytropic fluid. Now, in the elastic case, that is not true. In the elastic case, we instead have this theorem that the Stoyanich function of any generalized polytropic elastic constitutive function for spherical symmetric bodies must have this form. Yeah, there are two possibilities here, where if gamma is different from 1 or gamma is equal to 1. Okay, so gamma here is this exponent that appear in this scaling property. And so it is defined uniquely up to the choice of a function S of this variable delta over eta, which I remind you is what I call the shear variable, and the shear function should satisfy this property. Okay, so this property here, the first three equations are just the compatibility equation with linear elasticity, while this equation here for this stored energy function, well, this is the global hyperbolicity condition. It's a convexity assumption on the shear function that ensures that this model is globally hyperbolic. And so now, what is the value of, so the value YB, the boundary value, the constant boundary value YB on the boundary of the body, right? So I'm assuming here that this CBS assumption is satisfied. So on the boundary of the body, the shear is constant, and it is a solution. This constant YB is the solution of this equation. Fyb equal -3 gamma to the power -1, where Fy is this function here. Okay? So since this function, by the hyperbolicity condition, this function is increasing, so there is at most one solution of this equation. Okay. So now these are still very general model, and it's very hard to work with this generality because, first of all, you don't even know if this equation has a solution, and secondly, even if you can prove that it has a solution, then you in general are not able to find an explicit value for this solution because this function here in general, very high order polynomial maybe. So but there are some other conditions that can be imposed on this function, on this shear function, that are quite natural. For instance, I can impose that to be just a linear combination of powers of y. So S is the function of y, and it chooses to be a linear combination of powers of y because it seems kind of natural since we are in a polytropic, in a power law model. And then in this case, plus some minor additional assumption that you end up with only one possible stored energy function, which is the one that you see here. Okay, so the freedom now, before the freedom was to choose this function S almost arbitrarily. Now the only freedom left is to choose one extra parameter beta in this stored energy function, which I call the shear parameter, and the exponents beta and gamma must satisfy this inequality. So beta must be different from 0. Gamma must be positive, and this is the important one. Beta must be less or equal to this quantity 3, 1 minus mu divided by 1 plus mu times gamma. And where does this condition come from? This comes from the condition that this equation here should have a solution, as I will show in a moment. Okay, so first let me write the constitutive function for the radial pressure and the tangential pressure that derive from this stored energy. So the radial pressure, the tangential pressure is a bit complicated, as I told you. Usually it's complicated, but the radial pressure is not so hard actually. It's just you see, it's clear that the radial pressure vanishes when delta over eta is equal to YB, and this YB in this model is given by this expression in terms of the parameters beta, gamma, and mu. So you see here that mu is important, right? So you cannot just set equal to 1. And the condition, therefore, that I had before, this inequality, is just a condition that this YB should be greater or equal to 0. And by the way, when I choose equality here, so beta exactly equal to this, then this is when YB, so the shear on the boundary of the elastic ball, is exactly equal to 0. And so this, if the shear is equal to 0, also the density is equal to 0 on the boundary. Okay, so that's the only case. For all other choices of these parameters, the density on the boundary of the elastic ball will be positive. And so these are essentially the remarks that I just mentioned. So also the fluid case, if you let mu equal 1/2 in this model, you just go back to the fluid case. Okay, so right. So then there are the other interesting, important property to mention is that this equation of state satisfies the Bacher-Erickson inequality. Okay? So it satisfies the weak Bacher-Erickson inequality for all admissible value of the parameter beta and gamma. Okay, and in addition, if and only if beta is bounded below by this quantity in the right hand side, then it also satisfies the strong Bacher-Erickson inequality. Okay, so this is the region in the gamma and beta plane where this is satisfied. So this line here, this continuous line, is defined by this equation here. Okay, so it's the equation, it's the line where if I choose the parameter on this line, the shear at the boundary of the elastic ball is 0. So the weak Bacher-Erickson inequality is satisfied everywhere below this line, and this is so for all models, right? Because I have to be below this line in this model. And it's also, the strong one is also satisfied in this shadow region, okay? And so let me show you now some results on static state balls. These are most, what I'm going to show today is mostly just some very simple numerical results. If I can do it, then it must be very simple. So I'm looking for which parameter of gamma and beta in my quantity function, this one. This static balls exist, so there is a finite radius solution of the equation. And so let me show first how this region looks like. So the shadow region, including the darkest one, are the value of gamma and beta for which it is found numerically that this static ball exists. And I give you here 4 different pictures because they are referred to different values of the Poisson ratio. And what happened here is you can see that there exists a curve, which I called beta star, and a gamma star, such that, well, this curve beta star at the value at gamma equal gamma star intersect this upper boundary. Okay, so, and if gamma is smaller than gamma star, then I need to require that beta is smaller than this beta star. But if gamma is larger than gamma star, then all values of beta are admissible. Okay, and this region has the same shape for all value of mu, as you can see here. So then the conjecture that I present here is that I believe, I mean, this numerical simulation are rather very simple to do so, and they are rather clear that there exists some beta star, as I mentioned, with the properties that I mentioned before, such that strongly regular self-gravitating polytropic elastic ball exists if and only if gamma is smaller or equal to gamma star, and beta is smaller than B star, or gamma is larger than gamma star, and then beta can be whatever. And so, and by the way, so this darkest region are the one where I can actually prove analytically that this balls exist. So you see that the analytical proof that I have is still very far from the conjecture. Also, if you take, so you can see, I mean, mu is increasing from here to here, and then from here to here, and then you see that this gamma star is also increasing. And when we approach the fluid case, okay, so mu here is 0.48 and the fluid case is 0.5, then this gamma star seems to converge to the quantity 1.2. And so in this limit, the conjecture that I just wrote here reduced to the, well, the proof, to the fact, not longer a conjecture, that these static balls in the fluid case only exist when gamma is greater than 6/5. Right, so this is what I just said here. Right, the last slide of my talk, is some remarks, again, numerical remarks, result on the case of homologous, say, collapse. So I don't really have much to say here. I mean, so this homologous balls, as it is known, there are 2 types of these balls, the one that are continuously expanding or the one that are continuously collapsing. Expanding balls are much easier to construct, even analytically. Collapsing balls are much harder. Even in the fluid case, it's not at all trivial. And in this elastic case, I wasn't able to prove anything so far. But numerically, it is evident that they exist. Okay, so I'm not even going to discuss much this because I don't really have a lot to say. Okay, so it's easy to find numerically that. So even in this case, by the way, I should say that one has to choose gamma equals 4/3. Okay, in order for have the right. So this critical value is the same as in the fluid case. You need this in order to have this type of self-similar solution. And they can be parameterized in many different ways. For instance, here, I choose the central density at time 0, and this alpha, which would be essentially the acceleration at time 0 of the boundary. So it's negative here because I'm considering collapsing ball. And then, so to have this solution here, the density has to be sufficiently large compared to this acceleration. But maybe the only thing I should mention here is that here, these curves are for different value of the Poisson ratio. Okay, for instance, mu1 here is 0, and mu2 is greater, it's 0.25, mu3 is 0.45, and as you can see, this region in this plane where this collapsing ball exists is becoming smaller and smaller. Okay, so and the fluid case would be some line here, which I haven't drawn. So what we can conclude from here is that, but that's not surprising at all, is that there are more solutions collapsing homologous ball in the elastic case than in the fluid case. But that's somehow it's not it's a very weak result, I would say. That is actually my last slide, as you can see from here. So I stop here and I thank you for your attention.
Thank you. Are there any questions for Simone?
Did you try to apply this for neutron stars?
You mean if I can do this in general relativity?
Yeah.
Well, so some things can be done, some others cannot be done. For instance, this homologous solution that will not exist, I believe, in fact, in general relativity, right? They only exist for dust. For instance, this polytropic, this storage function is exactly the same in general relativity, right? So it doesn't, because I expressed it directly from the beginning in terms of the density. So in general, so even in the fluid case, in general relativity, if you express the equation state in terms of the density, then it's exactly the same as in the Newtonian case. So then I would say that this model should be precisely the same also in general relativity. Then, of course, even proving, so here, as I said, it's like results like this, numerically, of course, it can be done also in general relativity, but analytically, I mean, it's much harder than in the fluid case. Of course, if you look at the general relativity case, then it becomes even harder, because then you have more complicated Einstein equation with a more complicated elastic models, and two complications usually don't cancel. Is it what you want to?
Yeah.